Hello and welcome to the fourth part of our tutorial series on GUI and app development using model-based design. In this part, we will go over how to develop the control logic of graphical user interfaces in Simulink. You can think of the control logic as analog to back-end in web development. This part does require previous knowledge of Simulink and Stateflow. Let's open the directory for the tutorial project that we have been working on, and let's open the model file. We can see that we have a QML setup block, two QML signal blocks, and a QML method block inside one of the subsystems. Now let's launch the Simulink library browser and go to the EGS library. We will go through these blocks one by one to see their parameters and discuss how they work. Let's start with the QML setup block. We use this block mainly to define what is the root QML file for our project. This file needs to be on the same directory as the Simulink model. There is a convenience browse button that will list the QML files on the directory. The checkbox below is to slow down the simulation to approximate real time. There is a new feature in Simulink 2018A that will allow you to do this, but if you're using an older version, then you have this setting as an alternative. The last button will display the license agreement for EGS. Now let's open the Get Property block. This block is used to read QML object properties that have compatible types as discussed in the previous part of this tutorial. We need to provide the object and property name and the type of the property. The browser button opens an object tree browser that simplifies the selection of the properties. Just double-click on the QML engine icon to expand it, then browse to your desired object and property and select it. The object name, property name, and type will be automatically updated with your selected object. The next setting applies to QString, QColor, and QURL properties. Strings in Simulink are arrays of the type uint8 that represent ASCII characters. So this parameter is the maximum length of this array. If the string is longer than this value, then it will get truncated. We will talk about strings a little bit more in just a little bit. Finally, the last parameter is sample time, and its behavior is consistent with other Simulink blocks. -1 means inherited sample time, which should be the right value for most situations. Next, let's check out the setQML property block. The parameters are almost identical to the getQML property block, with the only difference that this block can accept variable length input arrays. This feature only works with other blocks that support it, such as the switch block. Please refer to the Simulink documentation for more information about variable size arrays. Now let's open the QML signal block. We see that this block has less parameters than the property block, and only the object name and signal are needed. We need to specify the signal arguments for proper signal identification, but as we mentioned before, we do not have access to the arguments from Simulink. The easiest way to specify a signal is to use the signal browser. We can see that the arguments are already included. Finally, we have the sample time. This has no effect on the signal block because the signal block is asynchronous, and this will probably be removed for future versions of EasyGUISim. The next block we're going to check out is the method block. We have two parameters as with the signal block, but we can't specify any methods with arguments. We also have a method browser to simplify the selection. Finally, we have a sample time parameter, which again has a behavior consistent with other Simulink blocks. The last block on the top level is the EGS printf block, and it formats and concatenates inputs into a single string. Before we go any deeper into how this block works, let's talk about what are strings and how they work in Simulink. As we mentioned before, a string is treated as an array of unsigned 8-bit integers that represent characters based on the ASCII standard. Every string needs to be terminated by an ASCII null character that marks the end of the string. The null character is represented by the integer 0. All array values after the null character are ignored. Therefore, to create a string constant, we need to convert the string to uint8 and add a 0 at the end. Let's go back to the printf block to go over the parameters and how the block works. The first parameter is a cell array containing the format strings that define how each input will be formatted on the output string. For example, %s means the input is a string and will be added to the output string unchanged. %e means scientific notation. You can add a number before the letter to specify how many decimal places to show. In this case, we're using 3 decimal places. %d is used to display integer numbers with no decimal places. Format strings follow the printf standard. There is a lot of information on printf on the web and even in MATLAB's help. The second block parameter is a cell array with the type of each input. Possible input types are double, single, int8, uint8, int16, uint16, int32, uint32, and string. The cell array needs to be the same length as the format string cell array. The next parameter is an integer array with the length of the input strings if there are any. This only needs to be specified for string input types. Others are ignored, so you should set them to 0. The next parameter is the maximum length of the output string. If the resulting string is longer than the specified length, it will get truncated. The final input is the sample time, which we have discussed in previous blocks. Simulink added native string support in version 2018A, and the compose block is very similar to our sprintf block. Keep in mind that to use the native blocks, you will have to convert between ASCII arrays and native strings. Now we can move on to the list model sublibrary. These blocks allow us to manipulate elements of a list model. Let's open a simple one such as the clear all items on list. This block has only two parameters, the list model object name and the sample time. This block has no inputs, and whenever it is executed, all the elements on the specified list model are deleted. The browse button works similarly to other blocks, but only shows list model type objects. The remove item from list and move item from list blocks also have the same parameters as the previous block, object name and sample time. The remove item from list block will delete the number of elements specified by the count input, starting from the element in the position specified by the index input. Indexes in QML are zero-based, meaning that the first element has an index of 0, as opposed to MATLAB and Simulink, which are 1-based. The move item from list block moves the number of elements specified on the count input, starting from the index specified by the from input to the index specified on the to input. The rest of the blocks are a little bit more complicated, but they are very similar among them. Let's start with the append item to list block. The first parameter is the list model object name. The second parameter is a cell array with the role names of the elements. And the third parameter is a cell array with the type for each role. The next two parameters are arrays used for string type roles. The first should be set to 1 if the input should support variable length arrays, and the second specifies the maximum string length for each input. The sample time works similarly to other blocks, and as before, we have a browse feature that facilitates selecting QML objects. This block will add an element at the end of the list with the role value specified on the inputs. The insert item on list block works exactly the same as the append block, but it has an index input to specify the position to insert the element. Finally, the set item values on list block changes the role values of the element at the position specified by the index input. These blocks have the same parameters as the append block. So let's do a few examples using the Simulink blocks to show how they are used. I have included a link to the QML files on the comments. For this example, we need to select the holamundo.qml file as our main file. Now let's remove the close method from the subsystem attached to the bottom click signal. Then add two property write blocks, a unit delay, a not block, a constant block, and two switch blocks to the project. Let's modify the block's properties to make sure that it outputs the correct type. And let's create a hello world string constant. Make sure you set the sample time to -1, or you will get some strange behavior from this block. Now let's make 4 copies of this block. Then let's change the strings as shown. And connect all the blocks together. Now let's use the property browser to find the right properties. And let's change the block parameters to match our needs. When we execute the simulation, it should show the strings in English and translate them to Spanish when the button is pressed and vice versa. You'll find that you can achieve the same results using very different approaches. So let's try using the new compare blocks from Simulink to achieve the same result. Let's pull in a new property read block and the appropriate string blocks. Then let's change the parameters and wire them together. We see that we get the same result. Now let's go back to the top level of the model and change the QML setup block to factorial.qml. Now let's delete all the blocks except the outText property block. And let's add some blocks to calculate and output the factorial of a number. We haven't seen the sprintf block in operation, so let's pull one into the model. For the sprintf block, see that we have an integer, a string, and a double as inputs. Once everything is correct, we try the simulation and we see that we get the output we expected. Next, let's play with the list model blocks for a little bit. We have included a QML file called list model blocks on the link provided. We can see that here we reuse the button component extensively. We also take advantage of property bindings to have this user interface look good in different sizes. Note the use of row and grid objects to help with positioning. In general, this is a good example to help you understand the QML concepts we presented on the previous section. Now let's go back to Simulink and create a subsystem for each button. We will go through this very quickly since there isn't a lot of new information. Now we can run the co-simulation and see each list model block in operation. We have included the resulting model file on the link provided. Up to this point, we have been doing relatively simple operations in Simulink, and if you have some programming background, you might be thinking that all we have done can be done directly in QML by using signal handlers. This is true for simple UI interfaces, but as a UI or app grows in complexity, then it becomes exponentially harder to manage. This is especially important when you have to handle signals differently depending on the state of your application. For example, let's say that you're building a smart home controller and need to communicate with several devices such as switches, thermostats, etc. using the network. You probably want to reuse the same network object, but realize that you need to do different things depending on the device that you're communicating with. You can create a network object per device, but this will increase the size and complexity of the application and affect the efficiency. You can also create a variable to keep track of the device you're communicating with, but you can imagine that this can snowball and quickly get hard to manage as you add more devices and features to your application. Many good software developers use state machines to simplify the mental model needed to manage these complexities. As you might know, Simulink has Stateflow, a state machine modeling and code generation tool that can simplify the process of implementing complex algorithms without having to manually code them later. We are going to implement a simple state machine to show you how to interact with QML using EJS blocks in Stateflow. Let's do a state machine that is functionally equivalent to the translation example we saw earlier. We need to add an input signal. Then add two states and a function called writeEnglishStrings. Then we will go into the function and then add two property write blocks. Then a constant block, and let's change the object properties for the property blocks. And then let's browse for the appropriate object properties for the property blocks. And then update the rest of the parameters. Now let's change the parameters of the constant block and copy it once and change the string. Now we go up and copy the function, change the name, and change the constant strings inside. Then let's add transitions and the function calls. And that's it. Now we can run the co-simulation and see that we have the same behavior as before. You will have to add Simulink functions to be able to add any EJS blocks. The examples included in the EJS installation have more complicated state machines that you can use as references. This is the last subject we needed to cover on this part of the tutorial. At this point, we have gone through the most important subjects in EJS, and you should now be able to create and co-simulate your own user interfaces and apps. Please feel free to contact us at support@mbdapps.com if you have any questions. Thanks.